Afternoon, everyone, and thank you for joining us for today's science session, Look Inside Methane Measurement at Landfills, a Controlled Release Study. So I'm Susie Boxman. I'm the Director of Programs at the Environmental Research and Education Foundation, where I manage the different research that we fund and do internally. And I'm really excited to be moderating this webinar today, where we get to hear more from Dr. Dave Risk. A couple of housekeeping items before I turn it over to Dr. Risk. So you can submit questions anytime throughout the presentation using the Q&A icon at the bottom of your screen. And then tomorrow you will receive an email from Zoom that has a link to both the presentation and a survey where you will be able to download your certificate of attendance. And with those couple of items, I'd really like to introduce Dr. Dave Risk, who is a research chair in climate science and policy at St. Francis Xavier University in Nova Scotia, Canada. Risk's FluxLab team has been involved in ecological gas measurements projects from pole to pole. He's visited over 15,000 onshore and offshore oil gas facilities across North America to assess inventories and has measured methane levels at Canadian landfills from coast to coast. So we're really excited to hear about the work he is doing related to methane emissions in landfills, and I'm going to go ahead and turn it over to you.
Great. Thanks, Susie. Can you hear me okay?
Yep, can hear you great.
Great, thanks. So I've recently begun working with EREF, and I'm always so impressed with its solutions focus and its ability to reach people with practical applications of science. And so I think that the reach and the engagement is the thing that impresses me the most about EREF. And I know dozens of countries represented on today's webinar list. And so I just wanted to thank you all for coming and for your interest in the research that I'll talk about today. So I'm a faculty member at a primarily undergraduate institution in Eastern Canada, and industrial emission measurement problems have been something I've been working on my whole career. And as a team, the FluxLab team has found a niche in large-scale studies from the measurement-based inventories that Susie mentioned to national landfill surveys and to the full-scale controlled release experiments that we're doing to test methane technologies for landfills right now. They'll be talking about now. So anyways, before I start, I just wanted to recognize EREF for funding the work and for WM's really important role in allowing us to use one of their sites. So this work is wholly industry funded and motivated. And also I'd like to give a shout out to Tarek Abishu who's been helping us as co-PI in the last round of experiments. So methane has been, of course, rising in prominence as an issue in the waste sector and accelerating in its move to surface over the last few years. And that's motivated by a number of factors like disclosure, new regulations across North America, regulations being renovated, global methane pledge and national targets, and technology is also part of the story. So we have progress in investments in methane measurement solutions in the oil and gas sector, and some of those are transferable to the waste sector, but we have much more available to us now than we used to. And we often identify these technologies by platforms. And so I have examples on the screen of aircraft and robots and trucks and drones, and there are others as well, of course. But we'll talk in more detail today about what those platforms represent and what the measurements look like from some of these measurement tools. So what do they do, and are they better than what we've been using in the waste sector? Which ones can we use? And certainly, images like the ones on the left are changing the conversation in the waste sector. So these are captures from Carbon Mapper as shown in one of the latest publications, and of course to show emission plumes of methane over landfill sites. So let's start a little bit with what they do. So it's a very simple slide, and I just wanted to point out the difference between the actual measurement sensor itself and the platform, which is how we often identify the tools, and then the outcomes of the measurement and whether we require some type of post-processing or not. So on the top layer of this slide, we have a number of different sensor types. So you see spectrometer, LiDAR, metal oxide sensor, and flame ionization detector. These are among the sensors that we use for measuring methane at landfill sites and oil and gas sites as well. And the spectrometers are by far the most popular type of measurement tool that we use, or the measurement sensor. And so spectrometers come in different varieties, so they can be open cell or closed cell. So that is that they have a laser inside of them normally that's measuring the the gas of interest, in this case methane. And so the laser can be passing through air, or it can be reflected in a closed cell, or maybe the sun is the light source instead of a laser. So these are all different types of spectrometers that we can mount on different platforms and have different types of resolution depending on the type of spectrometer. LiDAR is used in particular by one vendor. Metal oxide sensors are really common in some of those fixed monitors that we see. So those are the tripods that stand on surface, and flame ionization and other similar detectors are used for walking surveys often. So I'm already starting to talk about the middle layer and the interaction between the sensors and the way that we move them around. So based on the type of sensor and the kind of outcome we want, we have to move the sensor around in a specific fashion. So everyone's familiar with walking, obviously, and EPA SEM surveys, where we're covering the ground in paths of about 30 meters apart. And yeah, we can deploy sensors on all kinds of different platforms. So it's basically only limited by people's imagination. And so if we use the concentrations that we measure from those platforms using those sensors directly, the outcome is normally for detection type work. So we're using concentration as an indicator of emissions, so the emission presence. And we don't necessarily know much about its severity, because the concentration that we measure at a given point is a function of the leak severity or the emission severity, but also the wind as well. So wind has a huge influence there. And so anyways, we get a detection. So we get a positive or a negative. And if we want to go one step farther, and if we want to quantify the emission, that is to determine its rate, not just its concentration, then we have to take wind into account. And there are a variety of different post-processing routines that are used by the different sensor and platform combinations. So the one on the left, the GDM, that's the Gaussian dispersion model, and that's been around for many, many decades. It's a little bit older than I am. And we also have screens. So these are what we call flux planes, or imaginary curtains that were hanging in the air downwind of emission sources and allowing plumes to pass through them. So we can use various aerial techniques to measure in screens, or you can use tracers or time domain Gaussian. Anyways, we use those additional post-processing tools if our outcome is quantification. And so really there's no best technology, I'll say that right away, and maybe that'll be one of the questions that we get asked. Is what's the best technology to use? So they're good for different outcomes under different circumstances. So satellite, for example, doesn't work on cloudy days or at night. And so if you have a site that has a lot of cloud, and especially times of year when days are short, then that might not be the best measurement tool. But it might be great for other sites that have different circumstances. Okay, so I think that there are a few challenges related to understanding technologies and where they fit, and then challenges for the technologies themselves as well. So the first challenge is maybe thought paradigms. So the way we think is the first challenge. So for many of you, your whole career, EPA's told you to measure emissions over there using walking surveys because that's what's emitting. So we don't know how much it's emitting, but we understand emissions come from there. That's why we require measurement. So on the left-hand side, so these are images from some of the surveys we did at Canadian sites. We hired SEM contractors to come to site, and the sites are indicated by the black lines, the perimeter lines. So that's the whole site. And then the red areas, the red outlined areas, are the areas with the highest emissions. And then the colorful areas are the areas that were covered by SEM with the concentrations indicated by the color. And so, except for a few instances, except for closed landfills, and you can tell which one that is, these SEM surveys rarely covered more than 2/3 of the site, and they don't cover the areas with the highest emissions. And so at the right, we have pie charts that show where the highest emissions often come from. And on the top left, that's a closed site, but the dominant orange color in the pie charts on the right-hand side are the active working face. And so the active working face is, it probably on average is maybe about half of site methane emissions, but depends a lot on the life stage, the waste in place, the operational tools that are used by the landfill operator. And so last weekend, I think it was maybe on Sunday, that there's a paper release from Tia Scarpelli at Carbon Mapper, and it emphasized some of the same patterns, but I'd already inserted my own data into the presentation by then. But in general, we lack broad understanding like this because we haven't been able to use a lot of the measurement tools. And so anyways, I witnessed a sea change for sure in the last year within the North American waste sector where everyone's moving forward and reshaping their expectations thanks to measurement and increasing their levels of trust in new measurement tools, and they're helping us learn new things. So the second challenge, and this is the challenge that's more applicable to the actual measurement technologies or the vendors that are selling the measurement tools, is just the complexity of these sites in terms of emissions. So I've worked in oil and gas for many years, and oil and gas sites emit in relatively simple ways from one or a few pipes. And landfills are just much more complicated with different sources contributing over very large spatial scales. So we do have point sources, we do have pipes contributing sometimes, or tears in the cap around landfill gas wells, or we can have area emissions from the active phase. That is a big, broad area of emissions where emissions aren't coming from a concentrated point, but from a large spatial footprint. And so when we're measuring methane at landfills, often there might be methane coming from the background as well, and that can be confusing. So this is definitely a challenge for some measurement vendors, is just the scale of the sites and the complexity of the sources, source types. Another challenge, again, for the measurement vendors and measurement technologies is that landfills are topographically complex, and they're topographically complex and large enough that they have their own micro weather. It's like a small mountain range. So in the graphic, I have orographic lifting, as we call it in earth sciences, where basically same thing happens over the Rocky Mountains as the winds come off the Pacific. They get lifted up, and then there's heat sometimes that comes from the landfill itself that might contribute to plume rise if we don't have strong lateral winds. And on the backside, on the lee side of the landfill, we have these turbulent eddies that mix down the emissions that might be rising in the center of the landfill and actually tend to keep them towards the ground, which is surprising. So this situation presents a challenge for all of the post-processing methods to quantify landfill emissions for Gaussian, for mass balance, and others, because wind is the multiplier in all of those. And if the wind is so different at different points of the landfill, what's the wind input that we put into some of those solving models? And even in the near field, emissions from ground sources are kind of anecdotally different than for above ground sources that we see in oil and gas. So anyways, there are definitely some challenges here for the measurement vendors themselves. Okay, so just summarizing a number of the key measurement related problems. We have the scales, dispersed sources occasionally have high magnitude, complex wind-driven patterns, ground origin releases that might behave differently. And then I think we also have antiquated regulatory methods that don't really allow us to understand what the landfill is doing if we're just following the basic prescription. So And this is really where controlled release testing comes in. So we have all these measurement tools. We have measurement. We know we have challenges, measurement challenges, and we know that we're challenged to think differently as well by looking at and using the measurements. And so to test them effectively, test the technologies and methodologies effectively, we do have to set up controlled tests, and they need to be at full scale, and they need to be on sites that have the hilly topography, because if we were just doing this in a flat field, we wouldn't have those complex wind conditions. We need to have a multiplicity of sources, and they need to have different characteristics. They need to be point source and area source, so that we're basically creating a situation that's a representative of a real landfill. So we established with EREF's support controlled release testing site. And so I talk about it now as being a site and not just an experiment, because we've conducted 2 experiments now at the facility. So we call it the SimFlex, or the Simulation Facility for Landfill Emission Experiments. And it's a research partnership between my lab team and EREF and WM and Florida State University. And as I mentioned, it's wholly been funded by industry right now. So I'll just touch on, actually, I'll go back one slide for just a moment here. I just wanted to say that before I go on, that we did the set of experiments in November last year, and I'll predominantly talk about those today because I don't yet have results on the campaigns that we just wrapped up last week. So we just came out of the field, and there's some people that are newly back to campus. And I have included in upcoming slides link to the report. And I thought that would appear here, but I'll make sure that it's available in the other deck. Or did I just gonna flip back here, make sure I didn't miss it. Okay, I did not miss it. So anyways, we'll, in case I put it in a later slide, I'll just watch for that. But I'll talk about some of the details of the site today, and some of the basic results. Oh, sorry, I'm going in the wrong. There we go. Back to where I need to be. Yeah, so I'll basically give you the high level of the research results, and then I'll let you look for the real details in the report itself, or you can ask me questions if you want at the end. So it's an ideal site for controlled release studies because it's available, first thing. Second thing, it has very good cap integrity, and so the site has both a geotextile liner and clay on top. It's a 60-acre landfill, and it does have collection. So it's a very effective collection system and an energy project in the northwest corner of the site. This particular image was taken prior to the full covering, but it's now a nice grassy field. And we also have a very collaborative provincial regulator here. So anyways, we permitted the site for use in November 2023, and that's the set of experiments I'll talk about most today. So the controlled releases look something like a tanker truck with natural gas in it, and that's the star. So that's where our gas source originates. We're not using landfill gas from the landfill, but we're pipelining gas from a tanker out to various release points that are indicated in the white circles. And so the small white circles are point source release points. And again, they're all linked with pipeline. And those squares, or the pluses, I guess, the larger white circles with the pluses, are area-based sources. And so this is the experimental configuration we had for last November. And our total capacity was about 300 kilograms per hour, which is on the lower side. It's on the average side for Canadian landfills, probably on the lower side for American landfills. You just have larger population than we do. And we are also measuring weather at this site. And because there's so much interest from aerial and satellite operators in particular in this site, to be able to basically address their verification needs, we added capacity to the system. So we now have a capacity of 840 kilograms an hour in the newest installation. And I haven't shown you the release points for the newest installation because we're still waiting for submissions from some of the participants from the last few weeks' experiments. And we have more wind measurements because we really recognize the wind complexity is important. So this is what the site looks like. It's a beautiful place to work. It's been closed for maybe 7 or 8 years now. It's nice grass cover, and we're shallowly trenching in some areas for gas pipeline systems and area source releases. And so you can see some of the areas where we mowed the grass around release points from last year's study. So these are some drone pictures. So as part of the experiments last year, we had vendors that do different things. So we had some vendors that would do quantification, or that could do quantification, others that could do detection, and then some that were able to do both at once. And so amongst the quantification oriented vendors, we had some drones with tunable diode laser point sensors, and they were doing these flux curtains. So they were flying downwind, side to side, and up and down through the plumes. And they would use that curtain image to represent emissions, to calculate emission quantity, but they didn't know exactly where it was coming from, except that the plume was there. Mass balance, so that's a related technique that measures whole site emissions by flying around the site at increasing altitude with a manned aircraft. And then we have tracer correlation and Gaussian dispersion being applied by truck. So we had a number of teams using trucks for whole site quantification. Doing both, we had LiDAR and a satellite imaging sensor. And then on the detection side, we had the tunable diode laser drones that are shooting lasers to the ground, and the reflectance from the ground indicates how much methane is present underneath them. And then we had some R&D participants as well. And so R&D participants might be early on in generating a measurement solution for landfills, but are really interested to work at a site where the emissions are known because it gives them important developmental data. And this is where I have the link to the report. I'm sorry, I thought it was earlier on. So the QR code that's shown on the bottom right here will take you to the EREF's website and the final report. Okay, so we use a protocol for this work, which is the rules of engagement, basically, that's adapted from the Methane Emissions Technology Evaluation Center, or METEC in the US, which is a prominent oil and gas methane technology testing facility. And a number of things we had to do to adapt that. But anyways, we need to have these rules of engagement for all the measurement teams before, so they know how they're being judged, basically. And separate from the protocol are the experiments themselves. So we build experimental scenes specific to the vendors, and those scenes look something like certain sources being on, some not being on. All the sources that are on, of course, on at specific rates. And so, anyways, we build experiments for quantification and detection. Okay, so jumping right into some of the results, I think that something that was nice to see was the success of tracer correlation. And tracer correlation has been considered the gold standard for landfill methane emission measurement for some time. So it's an involved procedure. It involves putting tanks of acetylene on the landfill surface near emission points, turning those tanks on, and then measuring downwind the methane and acetylene at the same time. And so because we knew the flow rate of acetylene and the dilution to the point at which it was measured, we could apply some of the same transport characteristics across to the methane. So we don't even have to measure wind speeds or anything like that as part of the method. So it performed really well. And it's not an easy method to deploy necessarily, but it has very low bias. So the bias is indicated by the slope of the points relative to the dotted line. The dotted line would be perfect, and so it's almost perfect. And then we see some variability in the measurements. That some are higher and some are lower than the line, but in general, pretty tight relationship. So that performed very well and much better than the Gaussian trucks. And so the Gaussian trucks are not given the advantage of having a tracer to also measure. They only measure methane, and they measure methane downwind along with wind speed and direction. So it's easier to deploy because you don't need to access the site at all. But it has more inherent variability. And the work practice, the experiments were running very quickly, unfortunately, for the trucks last year. And so oftentimes they didn't really have enough they didn't have their normal work practice worth of repetition as part of the measurements. But anyways, we still see that there's bias, so they're typically under measuring. So you see that the colorful dotted lines are falling underneath the black more heavily dashed line. And so that indicates a tendency towards underestimation, and that there's also a lot of variability. So for any given measurement, they might be half or even lower than emissions, and then sometimes maybe on the next measurement they might be higher. And so I'll talk a little bit later about investigating some of these points where the techniques perform more poorly or better, because those are really the areas for development, the opportunities for development. So interestingly, these are two different truck teams, and both had very similar outcomes. And like I said, it's a cheap and cheerful technique, but certainly not as accurate or as precise as tracer correlation. So LiDAR also performed really well. This is an aerial technique from a helicopter in this case. And we have two colorful lines here because one of the interesting features of the LiDAR team is that they never came to Canada for the measurements. So they flew into Canada from Detroit. So the site is very close to Detroit, and made their measurements and flew back. And so what they didn't have is on-site wind measurements from ground stations. And so as part of our experimental protocol, we set up a procedure whereby vendors could submit numbers without the benefit of having any on-site wind measurements because they wouldn't normally have those. And then after that, we would give them the wind measurements from the site and give them the opportunity to resubmit if they wanted to. Because they need to use some wind speed in their quantification algorithms, but they're not necessarily informed about which wind to use. They might be using wind from a nearby airport or some other wind product that's proprietary to the company. And at any rate, in this case, we saw that when we provided the vendor with the on-site wind measurements, so that's in the orange line, that their measurements improved so that the bias was reduced, and they came very close to the one-to-one line. And the error bars for almost all of the measurements overlap that black dashed line, which would be perfect. And so, anyways, LiDAR was a very effective tool. It's because it requires a manned aircraft. It's not one of the ones that's lighter to deploy, but certainly those teams, especially if they have other work nearby, are able to do these site scans very quickly because in this case, every measurement point only took a few minutes of measurement to make. So they're very, very fast when they do arrive on site, and very accurate and precise as well. So for UAVs or drones that were doing these flux curtains. So this is, again, a tool where the drones would find, the drone operators would find the emissions. They have a small sensor on the drone to find the plume, and then they'd fly downwind, side to side and up and down through the plume to be able to basically map out a transect of the plume, or a cross section of the plume, I should say. And from that cross section, they can use their post-processing techniques to estimate the emission rate. And so I'm still talking about quantification tools here. So the team on the left had very little bias. So the one-to-one line falls right on the dark dashed line, but definitely some variability. So there are a number of points that fall off by 30 or 40%, but then many others are very close. And they did have error bars as well. The team on the right-hand side, again, very little bias if we average out the points, but we see that even though they were applying the same technique, there's more variability inherent in their measurements. And so it's harder to rely on an individual snapshot, but an average of a number of estimates might be just fine. And the team on the right did not provide us with error bars, which is something that I get asked about a lot. And so some vendors provide error bars and other vendors don't provide error bars. And we just basically assess what we're given. So I think that this is the most important slide because in summarizing some of the quantification results, because basically it provides comparisons and context as well. So I was in preparing this presentation thinking about the efficacy or the accuracy of first order decay models in comparison to measurements. Not to say that measurements should replace first order decay models. I think that there's still an important role for modeling site emissions, especially as a design tool and an inventory tool, because not everyone will be able to measure. But for first order decay models, I think we can say that we're doing pretty well if we were within 25%, and that I often read papers that say that errors can be even outside of 200%. And so I've provided these dark gray shaded areas to represent sort of our understanding of first order decay models. So they might be more accurate in some cases than 25% error, and sometimes they're going to be worse than 200% error. But from all of my reading, I think that those values kind of bracket the normal situation. And so I've plotted here measurement vendors from the last round of controlled release experiments and their quantification error performance. And so you see that many of them fall pretty close to that one-to-one line going up and down the middle. So that's zero error. And many of them are within 30 or 40%, or at least the edge of their measurements at least touch that one-to-one line. So 10 out of 11, they at least cross or touch the one-to-one line. 10 out of 11, almost all of them have less than 50% bias in the measurements. 5 out of 11 have less than 20% bias in the measurements. And so I think overall, my takeaway from this work, and I was in some cases pleasantly surprised to see this. I didn't know that we'd see quantification technologies working as consistently as they did, but in many cases, many of them are doing a good job. They didn't always get the right answer, but with repetition, we can establish a mean. And for each of these box plots, you may or may not be familiar with box plots, but we have the vendors on the left-hand side, of course, listed, and then we have these colorful horizontal bars. The colorful bars represent the majority of the measurements. The line in the middle of the colored bar represents the mean, and then the little hairs that extend out to the edge represent the total scope or total variability of the measurement. So we might have had one or two outliers on the very outside ends. But anyways, most of these come pretty close to measuring or to quantifying landfill emissions. The exception, I think, here, of course, are the blue bars, and so these are some of the tripod sensors. So they all have quite different performance relative to one another, and some of them were in the R&D category, but got put in here for interest's sake, because I think that this is certainly a tool that we'll see different performance from as we go forward in the future. So they're basically brand new for landfill applications when we used them last November, but I know that they've matured a lot, and especially as the post-processing algorithms that need work. But like I said, I think that they're going to come along quite quickly, and hopefully Simflex or the site as an incubator, and these experiments, if we can keep them going, will help bring along some of these technologies that are of interest to operators in the sector because they're very convenient and they can sit on site comfortably for a long time. So detection performance was more varied. So these were the tools that are where we're just using concentration and not quantifying. So LiDAR is the one on the farthest left. So they did very, very well. And so they had 100% true positive. So every emission they detected in the correct spot. And for some of the two drone vendors we had, and so they're using the column drones where they're flying above the surface and shooting a laser down to the ground. They're flying about 20 meters height in this case. They had a low number of true positives and quite a number of false positives and false negatives, which means that they're interpreting emissions that don't exist, or else maybe just detecting emissions but at the wrong spot, somewhere downwind of where they originated. And so anyways, the LiDAR was super sensitive and the drone column sensors were less sensitive. But, I think it's a valid question to say, what are we comparing against? And so how would have these drone column sensors compared to EPA 21, for example? So I think some of the most interesting things to me from these experiments are trying to figure out what we did wrong. And I'll tell you exactly what we have problems with in the truck, because one of the trucks was from my lab. And the landfill is pictured in blue here, the landfill polygon, sort of near the top center of the map. And everywhere that's indicated green, we're making measurements that were very close to the one-to-one line. And then the red area here is where we're significantly underestimating, which biased our results quite a bit. And this is where the emissions are coming across these forested areas on the way to us. And we're also very far from the landfill by that point. So that's something that we have to work on. And for some of the drone column sensors, if we map out dispersion from at 30-meter grid points, they were emulating the walking surveys. And so an example of the walking survey grid relative to an emission of 23 kilograms per hour is provided in the center of this image. And if we look at the legend of that image, it only goes up to 190 parts per million. So it's if a drone were passing nearby it, it might interpret the emission to be in the wrong location. It might be interpreted to be right along the path, and then it might have actually never even detected it at all because we didn't exceed 500 ppm. So anyways, we've done quite a bit of work investigating this a little bit more, and also the importance of gimbals and other sensor features. And I think that some of that work is starting to show, and we'll see how things work out in the next controlled release experiments. But by tightening up spacing, so we're now in these images at 7.5 meters instead of 30 meters, and you can see how many more measurements we get all across the same plume, and how maybe we shouldn't be tracking the 500 ppm exceedance points, but we should be imaging the plume instead and tracking it back to origin. And so we see the sensors on the left-hand side are also working very well. And these are some results presented at an EPA workshop recently, showing that we have fairly low coefficient of variation. The sensors themselves seem to be working well. It's the work practice. So the next steps, just to conclude here, we have just wound up experiments, and we are focused a little bit this round on different technologies than before. So we're focused a lot on SEM, and we did walking SEM as well in the latest round of controlled releases, a lot of walking SEMs and drone column sensors. We had satellite participation, as well as many, many continuous emission measurement tripods. So these are the stationary sensors, truck and also enhanced wind studies. And then in the spring, we'll have an extended aerial, satellite, and aircraft, and also the drone FluxPlane campaign, including some of the others as well. But we'll catch those in April or May under better weather. So anyways, I just wanted to thank our team. It takes a lot to build and operate sites like this and to get them permitted. So I especially want to call out Philip Buntov and Rafi Hussein and Yuri Dudak. And then, of course, thank again EREF and WM for their support of this work. So anyways, if you'd like to contact me, my contact is at the top left in our lab LinkedIn, where we post results of many of these studies. It's on the top right. And yeah, I'll just leave it there. If there are any vendors in the room that want to participate in the releases next spring, just please reach out to us.
Awesome. Thanks, Dave. So we also dropped a link to ERAF's website and the report that a link to the report there if you'd like to access the report if you missed the QR code that Dave showed earlier in the presentation. Thank you so much. So I definitely have a few questions that had come in. I think one is pretty relevant to the experiments that you guys just wrapped up. So one person was asking, how have you been able to do measurement during the winter? Or what, maybe it's more of a question of what challenges have you faced with winter measurements, and what do you think could be done to kind of mitigate some of these challenges?
Yeah, that's a great question. And obviously winter is something that we're pretty accustomed to in most parts of Canada. And so in the wintertime, we definitely keep measurements going where feasible. So we've worked in oil and gas all through the winters for many years, and we're primarily using truck tools, drone tools. Drone techniques work as well, as long as the temperatures aren't too cold for batteries. I'd say that the main tools that don't work as well are the imagers or anything that needs to bounce a laser off the ground. So those types of spectrometers have interference from snow on the ground. The snow absorbs the wavelengths of interest to them for detecting methane. And so satellites and aerial imagers and others aren't generally able to measure in snow. There are some exceptions, and I know that vendors are working on it as well. But those are the ones right now that they're sort of no go. But many of the other tools that we normally use are no problem in the winter, and even in the hard rain and things like that. Truck tools work well. Drones won't, obviously, but
Yeah.
yep.
Thanks for that. So I guess another climate related question. Have you all had any discussions about doing these types of studies in other climate locations?
So we haven't been in discussion about that, but they are common as well in other places. There's another controlled, the METEC controlled release site that I referred to previously is in Colorado, and that's obviously a very dry location. And one of the other controlled release sites that's very interesting is run by Stanford, and it exists in the desert, maybe in Arizona, I think, and it's specifically for testing satellite tools. And so warm and hot, and we can definitely apply ground tools at the same time. They're the same tools that are useful in the winter or useful in the summer, and then in dry places you additionally have all like year-round use of the tools that are image-based and can work quite well on dry surfaces.
Yeah, but to clarify, for those existing sites, though, they're not landfills necessarily. They're kind of really just testing sites in different climates.
Yeah, they're just testing sites in different climates, but certainly if the measurement tools work at testing sites, and many of our oil and gas sites, you have to remember, in the US are pretty far south, and they're pretty hot, and all of these tools play in those environments as well.
Gotcha.
Yeah.
And then I just think, just to add to that, so EREF is looking at potentially funding some additional landfill emission related work at a landfill site in the southeast US. We're still working out the details on that, but are hoping to do some additional work there as well, since I think we do really need to understand multiple different climates to really pinpoint how these technologies work across the North America.
I agree. And the efficiency of doing that there's an important efficiency to doing that, because in our climate, we also have a lot of cloud because it's humid environment, and it means that and also just more weather and wind and some of the aerial techniques, even if they don't depend on cloud or cloud limitations, that they still can't fly in too much wind, and so we have that problem. The winds have to be just right, and I think calm wind situations are really interesting. I think that there's a real efficiency in testing the satellite tools in those clear sky environments. So it's just much easier to depend on every shot being successful.
So here's a question. I'm not sure if the work you've done can answer this, but maybe even your previous oil and gas experience can contribute. So the question is, have you noticed a change in the volume of emissions changing with incoming high pressure and low pressure systems moving in?
So I think that that's a question related to the influence of atmospheric barometric pressure on landfills, and I think there's some great work out there already that shows that those pressure fluctuations can be quite high at sites that don't have capture systems, and so at sites that do have capture systems, they have a mechanically regulated pressure environment in the subsoil, whereas sites that don't have landfill gas capture are basically subsurface that's connected with the atmosphere. And so we have certainly seen that in our measurement campaigns across Canadian landfills, that on low pressure days or days when the pressure is tending lower, so the landfill gas expands, and it basically the poor air comes above the surface, pops above the surface, swept away by the wind. That represents extra emissions. And under high pressure trends, the opposite is true, where the atmosphere pressure in the atmosphere is high and is driving into the landfill, and that retards the rate of emissions coming out of the surface.
Interesting. So another question, just thinking about the controlled release experiments, landfills obviously have background methane emissions. So how did you control for those in these experiments?
Yeah, it's a great question. So this site is special in that it has, like I said, very good cap integrity because it uses both clay and geotextile on the surface, and it has a very good capture system as well. So we've done SEMS across the surface and other types of measurement, and we find that all the central parts of the landfill are basically emission free. There are some small emission points around the sides, and we have a very good idea of what they are in aggregate, and that's published in the report. In addition to the flare slip or the combustion slip, sorry, at the electricity generation facility at the northwest corner of the site, because not all landfill gas can be burnt. It's 99, those furnaces are 99, 98, 99% efficient. And so we have some degree of slip there too. So yeah, in aggregate, the emissions are very low. They're in the 20 to 30 kilogram an hour range. So we have to know those very well and where they are to be able to judge participants in the proper ways though. Yeah, great question.
Yeah. Let's see. I think so. I think this is mostly related to the truck-based measurements. But the question is, if the release duration were longer and measurements more frequent, do you think that the truck results would improve? And would this reduce the variance and mitigate the underestimation bias in the mobile surveys?
I think the underestimation bias is a function of that the forest to some degree in between our receptor area and the landfill itself, and maybe the algorithms a little bit too. I think what happens is the emissions dance across the top of the forest, and they don't really enter ground level where we measure them. So they might be moving just above us. And so anyways, that's something that tracer correlation didn't have a problem with. So maybe the trucks can get better there too. So I'm not sure that it'll reduce the bias unless that gets better. I think it'll certainly reduce the variability to have longer measurement experiments. And so we did that this time in the latest round of experiments because that was a shortcoming of the first round. So we did 71 experiments in 10 days or something like that. And this time we did more like 40. And so we allowed the trucks to use their normal work practice that involves a certain number of repetitions. And so we'll see how that works out. So yeah, even when we participate internally as a vendor, there are certain people from the lab group that aren't allowed into conversations, and yeah, we're all of this data gets hidden in a particular silo.
Absolutely. Yep. It's secretive in a sense to make
Yeah,
sure
it's
everything
fun.
is not biased.
Yeah, it's fun.
Well, let's see. So there's a couple more climate related questions. So somebody is asking, do you think you could replicate the testing in tropical climates such as the Caribbean?
I certainly think so. So controlled release experiments are fairly easy to build and set up. There's certain level of expertise in dealing with the dealing with the pressures and reducing those from tanker pressures. If natural gas is available on a grid, that's even easier. But for sort of setting up pipelines and flow controllers and to be able to do the experiments themselves, they can be done anywhere. There aren't as long as there's a supplier of gas that's willing to bring it to the site. And at landfills, we do need trucks though to do it. We can't just use gas cylinders as they can in some of the oil and gas test centers.
So, and then do you think maybe a question would be, how do you think you would carry out these sorts of experiments, or I guess even measure methane in rainy climates like the Caribbean, or just in instances where there's a lot of precipitation? I mean, does that impact how the methane is moving into the atmosphere? How do you think you could kind of mitigate for the additional precipitation, either as rainfall or as snow?
Yeah, so rainfall will definitely impact the surface porosity and may, on one hand, kind of block up some of that porosity, but on the other hand, it's displacing the water percolation, maybe displacing some poor gas from areas that aren't covered, and so that'll be doing the opposite. That'll be pushing gases up rather than retarding their emissions. And so I don't know exactly where I'd fall on the temporal variability of landfill emissions as a function of rainfall events, but it certainly having rain certainly restricts the available measurement tools. And so if one were to do measurements in those situations, so there are much narrower range of technologies that would be available. So you have the on-site continuous monitors once they're proven, and at some point that they will be. You have trucks, maybe some of the ground robots, and then walking tools as well. But a lot of of course, tools that we put in the air are not very functional in those types of environments.
Yeah. So a question just came in about drones. I think you covered some of this in the beginning. What kind of sensor do you attach to the drone? But I think also, how do you deal with the issue of payload, since drones kind of have a maximum weight that they're going to be able to carry?
There are a variety of different types of sensors available for drones these days. So they might be point sensors where we have a small tunable diode laser cell that's small enough to be a drone payload that weighs maybe a kilogram or a kilogram and a half or less. And so number of places you can get those. And we also have the column sensors, and the column sensors are a little bit lighter weight. They're, I think, half to 3/4 of a kilogram, and they have an active laser source that bounces off the ground, and so they can fly from 20 or 30 meters high. And they're used for different purposes. So the point sensors are used for flux plane measurements, and the downward looking lasers are used for SEM type measurements across the surface.
Well, I don't have too many questions left. I think one good one to kind of end on is when do you think the most recent results will be available?
So I've promised to have them available by the time that the ERAF summit comes in March. And so, Susie, you can chat a bit more about that if you like. But I will be presenting some of the newer results at that session.
Yes, well, thanks for that plug. So just so people know, EREF is having a 2025 summit on landfill admissions, and it's going to be March 4th and 5th on Raleigh. And now you know that there'll be some of the latest controlled release results will be available by that summit, as well as a lot of other really good information should be available for that. And then I think with that, just check and see. Um, I think that concludes today's science session. And so we'd like to thank Dr. Risk for his time and expertise, and to all of you for joining us today. We hope that you'll be able to join us again in 2025 for more free and informative science sessions. As a reminder, please look for an email tomorrow from Zoom. That'll have links to the presentation, a brief survey where you can download your certificate of attendance. I would really appreciate your feedback so that we can make sure we're providing you with content that's usable, and so you can help us improve our science sessions. And so thanks again for attending, and we hope to see you in the next one. Thanks, everyone.
Thanks.
Thanks, Dave.